Welcome to this another introductory lecture on high temperature materials. So this would be possibly the last lecture on the introductory module. Now if you are wondering or rather fed up with too many lectures on introduction, you can feel happy because this would be the last one on introduction, and in the subsequent lectures we can get into the theoretical aspects of understanding how a material would behave at high temperatures. Now in this lecture the question that we want to address is, why should one invest so much time in studying high temperature material, or what is the need for studying high temperature materials? Now like all the rather broad questions or philosophical questions, this question can also be answered at different levels. So let us begin by answering it from a very primitive standpoint. Now the technological advancement, the ones we are experiencing, if someone asks you like you are in the middle of some sort of a technological change that is happening day to day, please explain it to me with an example. If someone asks you that question, please explain to me how you are experiencing the technological advantages or advancements. You could start up with a very easy examples like the mobile phone that we use, wherein when your elders were using such devices, or when you saw your parents or other elders using such devices, even you are young, you would have noticed that a major portion of the mobile phone comprised of what we now call as keypad, and only a small portion was dedicated to the screen. But now as the technology advanced, we find absolutely no place for keypads, and the entire mobile phone with its increase in size comprises of screen. One can also give an example of storage devices, wherein a few decades before the portable storage device we had was a floppy. The memory capability of it was around some megabytes, and then we moved to CD. Again, it was in the range of megabytes. Then we got used to DVDs. That's where we were experiencing, or we were using storage devices in the range of gigabytes, and then we had huge memory storage devices which were not really portable. And then eventually now we are in a place where even the laptop that we have can include SSD sticks of 256 gigabytes or 512 gigabytes, sometimes 1 terabytes. In addition to the internally built SSDs, you can also have external SD cards which are very small, that has the capability of storing around several hundred gigabytes of storage. So that is how for a short span we can measure the technological advancements. Now when one wants to see what are the technological advancements or how the civilization themselves evolved, like anthropologically, if you want to see, one way of doing that is by seeing the materials people used at that time. So from that we have our stone ages, copper ages, bronze ages, and steel ages that you can see in the slide here. So this does not mean that people used in the copper age exclusively copper, or in the steel age exclusively steel. It doesn't mean that. It means that like this was the preferred material that was used, or this was like easily available material or economically used material at that time period. So for instance, in the stone age, most of the materials that the man used at that time was made of stone. Please pardon me when I say man, I use it as a general neutral term. It doesn't mean that I'm excluding women here. It's just a general neutral term. It is synonymous with human. So, and also when I say copper age or any other age, it means that predominantly this material is used, or whatever other materials are used, the way the processing of this material or any other material is similar to the material that characterizes that age. Supposing in the copper age silver was used, the way the silver was processed or the way the gold was processed, it was not much different from that the way copper was processed, or the temperature range in which this processing was done, or the techniques that were used were not unique to the particular material, although in some sense it could have been, but generally speaking, the techniques that were used to process copper in that age was similar to that of, or the overall process was more or less similar to that of gold or any other materials that people used in that age, and that is the reason why we get that name copper age, and the same goes for bronze and steel age. Now, this different stages in our civilization or the progress of human race. Now, one can categorize the Stone Age from all the rest, because particularly from the standpoint of high temperature materials, in Stone Ages there was not much relevance to high temperature materials. The purpose for high temperature in Stone Age was mainly it served just two purposes. One was for cooking, and the other was for creating a heat source wherein the humans could warm themselves against harsh cold climates. Now, of course, during this period, humans, they would have realized that they could not use all stones for such high temperature application, be it for cooking or for creating a heat source that they could warm themselves with. So, the initial study or analysis of high temperature materials would have begun at that time itself. But a significant change came in the subsequent ages, be it Copper Age, Bronze Age or Steel Age. So, all the role of high temperature materials significantly improved in all these ages, because one cannot have any of these ages without involving high temperature into it. So, we need irrespective of the age, be it again copper, bronze or steel, irrespective of the age, we need high temperature for particularly two purposes. One is to extract the particular material from its ore. So, we have you might have been acquainted with the process of extraction. So, we have our ore and we need to extract the material that we are desired in from that ore, and for that largely particularly when you think about the ages we are speaking about, that involves a high temperature. So, in these ages it is impossible to get a material without involving an high temperature. So, the high temperature was involved first in the extraction of the material that characterizes the age. Secondly, to process the material to get a desired shape out of it, be it a tool or be it a statue, again we need to have a setup wherein we could raise the temperature of the material. So, we need high temperature for processing for the extracting the desired material from its ore, and we also need high temperature to make the desired shape out of it or to process the material that we have extracted. So, in all these ages except for the Stone Age, even in Stone Age we thought we just described that there would be some part in the in analyzing the high temperature materials, but in all the rest of the ages high temperature played a critical role in both extracting and also processing the material that characterizes that age. Now, when we talk about the high temperature playing a critical role, it means that there needs to be a setup that is capable of handling that high temperature. And if you want to have such a setup, then it would mean that you have an high temperature material to hold that setup together, that works, that behaves the way that you want to behave. All this will be possible only when you have extensively studied the high temperature materials. So, studying high temperature materials has been with us for a very long while, and they have served a very important practical purposes. Beyond that, they have helped us to use definite materials that eventually became the ones that categorized a particular age. So, if not for the high temperature materials or the setups that were built of high temperature materials that enable us to use copper, that enable us to extract copper, that enable us to form alloys like bronze, that enable us to form alloys like steel, that also helped us to process these materials into the objects that we desire, without such a setup that is made up of high temperature materials, again which is the end of studying high temperature materials, these ages or these progress would not have been possible. Now, this lecture would be like more of a storytelling. So it is important for you guys to get involved, or else given the times we are in, it is easy for you to fall asleep. So let us think for a while now. You can of course pause the video right now and engage in thinking. Now, what could be the next stage of such a advancement in civilization? What could be the next stage? You can of course pause and think for a while. Could it be age of composites, or could it be age of plastics? You can think. So if you have done so, let us proceed with the lecture. Now, according to my understanding, I believe the next stage which would characterize an advancement in the civilization, or that would be more of a paradigm shift, would be something I would like plainly refer to as a plasma age. The reason I would call this a plasma age is because now if you have been noticing in the world, we are moving towards a clean energy source. We have seen the consequence of using non-renewable fossil fuels for generating energies that for be it electricity or be it for our transportation purposes. We have seen both the advantages and disadvantages, and particularly nowadays people are growing up to the fact that the disadvantages that have been piling up for a while has now started to affect the climate. Now, so we are in a place where we are in search for a clean alternate source of energy. Now, in addition to the renewable sources of energy, be it wind or solar, there is also an extensive research that is being carried in the field of nuclear fusion. Like apart from the nuclear fission reactors which we have around us now, wherein the energy is produced by the breaking up of a huge fissile atom, the nuclear fusion involves the fusion, as the term suggests, the fusion of two light elements or two elementary particles, and this would give an enormous amount of energy, and this energy we can harness it for our sake, and that can be a primary source of energy in the future. That is where the people are heading towards in the nuclear field of research. Now, the temperature that a nuclear fission reactor generates is at the order of its ultra high temperature. It's in the order of 10 to the power 6 to 10 to the power 7 Kelvin or Celsius. It doesn't make a difference when you are in that order. So that is the range of temperature that a nuclear fusion reactor would generate. These facts you might be already familiar with. Now, the problem with creating such a reactor is that we don't have enough or a material that could withstand such a temperature. So when you are talking about a temperature range of 10 to the power 6 or 10 to the power 7 Kelvin or Celsius, what you are ideally talking about is creating a sun that is of your own, and you are applying to create a vessel for that sun. Now, that is quite an impossible task. But people have come up with a wonderful idea of using a plasma to shield the vessel from the actual region where the fusion happens. So what ideally has been planned is that you have a fusion center where the actual fusion happens, and surrounding it would be plasma, and the vessel would be the outer end of it. Now, this is the plan that has been adopted for ITER, which is being built in southern part of France. And the projects for this ITER are being given, or the projects have been distributed all over the world. Even India is contributing to this project on ITER. And one of the places I had the privilege of visiting was in Germany. There is a lab in Jülich, which is close to Aachen. Now, in this Jülich, they also contribute to this ITER, and they have been planning to build such a small setup wherein they could test the materials that can be used to build this vessel within which we have the fusion happening. Now, the whole setup is very small. It could be the size, it is just the size of a room, and they don't even do a nuclear fusion reaction there. They just wanted to see how much the temperature, or how much of a temperature we can increase the material that we are currently proposing to, or high can we increase the temperature of the material. And in order to make that study, that is like the whole lab for that study or whole setup is just a size of a room. For that, you have to build coolant setup, which is like the size of the entire department, or it cuts across like 1 to 2 kilometers, the coolant tubes and all the setups, and the building for the coolant is so huge, like it is the size of our department. So that is where the importance of the high temperature material comes in. So in order to, we know that we have a good place where we can extract the energy, but the limitations of our material, particularly the ones that deal with high temperature, we are not so familiar with that, or we don't have sufficient advancement in the high temperature materials. We need to build coolant that is like 100 times larger than the setup that actually produces the energy, and also more expensive than the setup that actually produces the energy. So if we are able to crack this lag, or this question of high temperature materials that can be used in fusion reactors, or that could sufficiently withstand the plasma that buffers the fusion and the vessel, then we enter into a new age wherein we could then like power the whole cities from the energy supplied by the fusion reactors, and then maybe we could call our age as a plasma age, and that would be one of the clean source of energy. So this is one of the one example that I wanted to share with you, wherein the research on high temperature materials is still relevant today, and still a question that needs to be answered. And if someone is interested in nuclear researches, you don't have to change your field and do fundamental studies of nuclear materials or quantums to get into the field of nuclear research. There are material needs in nuclear reactors that people are very much, which people very much desire to, they want it to be addressed, and we could serve a greater purpose when we sufficiently understand and study high temperature materials. So these are one of the ways that high temperature materials are relevant to us. One is, as we have seen in the previous slides, that they give us the characteristic materials that we use in our civilization. So apart from this, like specific material characterizing a specific age, even, today in our day-to-day life, the things we use or the applications that we use for our comfort, for our survival, even in that applications, the high temperature materials play a critical role. Let's see. This is also a major reason why one should look closely into the high temperature materials, because they are an integral part of the critical applications. Again, like in the previous slide, like I said, we are moving towards in the search of a clean energy resources, but that search might take some time. Even though we have answers, we don't have an economical answers that can be put into a practice on a large scale. Till then, we have to make the best or efficient use of the non-renewable resources that we have already with us, the power plants that we already built. We have to make an efficient use of it, and this efficient use of it, or making sure that we are using the sources that are with us efficiently, in this aspect as well, the high temperature materials will play a critical role, as we will see in the few minutes we will have a look at that. So high temperature materials, they play a critical role in catering to our energy needs, be it power plants that are supplied by coal or oil. Both these power plants, or even nuclear power plants, they have something called as steam turbines that convert the energy that these sources produce to electricity. And these turbines have blades and other components that are exposed to high temperature because of the steam that enables these blades to rotate. So when we have an efficiently working material as a part of the turbine, then the efficiency of the whole power plant increases. Now when you come to the nuclear power plants, we have fuel rods. These fuel rods comprises of the fissile materials, the actual fuels that are made into pellets and are fed into these fuel rods. And these fuel rods are a very important critical component that enable the transmission of the heat generated or the energy generated by the fissile material to its surrounding. And that surrounding ultimately heats up and generates the water vapor or the steam that then subsequently propels or drives the steam turbine that we have seen. So this fuel rod is a critical component of a nuclear plant. Now, the reason why we need to have a sturdy or a high temperature withstanding fuel rod is only when you are able to have such a fuel rods, you will be able to control the nuclear fission reaction, or else it will run out of control and this will turn into a small nuclear explosion. So, in order to avoid that, you need to have a sturdy nuclear rods, and these nuclear rods along with the control rods are fed into the nuclear reactors, and the nuclear reactions are controlled in this manner. Generally, we don't operate in the full capacity, even though we are able to create a huge amount of energy. We don't do that because the material or the high temperature behavior of the material or the lack of sufficient high temperature material limits us from using or from deriving sufficient amount of energy, even though it is possible theoretically for us to extract such amount of energy. And that is why we have a control rods that are fully operational in order to control the nuclear fission reactions. Now, in addition to the fuel rods that are a part of nuclear reactors and that helps us derive energy from these reactors, we have boilers. These boilers again would be a part of any power plants, and they help us based on the fuels that we use, they help us turn water into steam that ultimately will propel the turbines to create electricity. Now, these boilers and along with the rods and turbines, and they along with the high temperature they are exposed to, they also experience other conditions that might affect their life, and these conditions include both the stress that these materials experience during their operation, and also the corrosive environment that these materials are exposed to during their operation. And that is the reason why in this course we focus largely on not only high temperature behavior just to see how material behave when we rise the temperature or when we rise the temperature ambient temperatures. That is not the only focus of this course. That is the reason we focus on how, when combined with high temperature, when we combine high temperature with stress, how the material behaves, and we combine high temperature stress and a corrosive environment, how the material behaves. These are the factors that we would like to study in this course, and the reason for it is, in all these applications, it is not the temperature or the high temperature that the material is exposed to, but also a corrosive environment and also the mechanical stresses that are imposed on this material during the application. Now, if you have the habit of frequently going through the news, a few months before we had an explosion of a boiler in Neyveli, in NLC Neyveli. Now, this whenever you hear the term explosion of a boiler, it is nothing but failure of high temperature material. It could be because of a lack of maintenance or whatever may be the reason, but the bottom line is it is the failure of high temperature materials. So, when you have a greater understanding of high temperature material, you can also posit a way that would help the application to extend the lifespan of the material and to avoid catastrophic failures. So, this is one of the reasons why one needs to understand the behavior of high temperature materials, particularly under the condition of stress and also corrosive environment. Now, there are, in addition to like the energy sectors, there are other critical applications wherein the high temperature materials play a vital role. These includes transport services. Like historically more than the energy sector, it is claimed that transport services are one area which propelled the research on high temperature materials. These transport services, they are not just confined to road services, it includes aircraft, marine and road, and in all these services, irrespective of their mode of transport, high temperature materials are involved. Let's just see the role of high temperature materials in because since we are already familiar with what would happen in a two-wheeler or in a four-wheeler, we have seen we have some vague idea of what an internal combustion machine is, and we know that in that combustion machine there is a rise in temperature, there is a controlled explosion caused by the fuel that we give. So since we are fairly acquainted with the happenings around the internal combustion or in and around the internal combustion machine or engine, we will just try to focus on the critical propelling factors in aircraft and marines. Now in aircraft and marines, the component that propels these huge machines or huge vehicles are these gas turbines. These gas turbines, some of you might know or some of you might not. So let me give you a brief overview of what these gas turbines are. These gas turbines, they comprise of three components rather. So one component is referred to as a compressor, and the other component is a combustion setup, and the third one is the turbines, the actual turbines. So here you can see, so here you can see that there is a compressor setup, which is then subsequently followed by a combustion setup, and then you have your turbines. Now what happens is that in the compressor, the compressor actually pulls in the surrounding air and compresses it and forces it into the combustion. And in the combustion, what happens is that based on using the fuel the fuel that we adapt to propel a particular machine, that fuel will be injected and a control explosion will be created, and this explosion would then empower the revolution or empower the movement of the turbines that ultimately would propel your vehicle. So this is what happens in the gas turbines, or the turbines that we use in both aerospace application and also in marine. So what we have a compressor that introduces air from the surroundings. We have a combustion setup that actually creates or raises the temperature of the air, increases its kinetic energy, and this air is then again sent to the turbine setup, which then rotates and propels the vehicle forward. Now, in addition to the turbine and also to the combustion setup, the entire vehicle is affected or experiences a high temperature or increase in temperature. And this temperature, along with increase in temperature, as we have seen in the boilers and other fuel rods or other setups wherein the temperature increases, even in this setup, along with the temperature, the mechanical stresses associated with it also increases, and also the environment to which the materials are exposed to becomes rather more dominant. They become more corrosive in nature because the temperature is being raised. So we need to have an efficient or an optimal choice of high temperature material so that these turbines could work efficiently. If we have such an efficient material or the apt material for these gas turbines, there are three ways in which this could serve our purpose, or this could be more advantageous for us. One is when you have an efficient material operating or being a part of this gas turbine, it would mean that the energy consumption is largely reduced, and that would mean the whole the transport phenomena or the whole option of this transportation mode becomes more economical. So it becomes more affordable. When you have a right choice of materials that would improve the efficiency of this gas turbine, then it would mean that this particular mode of transportation has become more economical and affordable. Secondly, in addition for it being affordable and economical, we are using the available resources to us in an efficient manner, and we don't have to worry about wasting or operating at a below par capacity. So when you have when the materials that we use are of the right choice, we can be sure that we are operating at the full capacity. Thirdly, it also improves the load pulling capability of the whole transportation system. That means the efficiency as a whole can be increased. So supposing you have a material, and because of the material properties, you are not able to impose or extract a load pulling capacity of a certain degree, and you change the material and the load pulling capacity increases, this would mean that you could then increase the size of your vehicle, and thereby making it viable for many, and also ultimately you would be optimally using your resources. So high temperature materials in the realm of transport services plays a vital role in not only ensuring that we use the available resources to us in an efficient manner, but it also helps us making the services affordable to everyone. As a matter of fact, there is a wonderful article by Professor Wood wherein he relates the analysis or the role of high temperature materials in creating more employment opportunities. So this study of high temperature materials is not totally irrelevant, it's not totally purely theoretical. They play a critical role in our day-to-day life, and if we are able to focus more on this high temperature materials, we can cater to these needs that not only improve or improve the way that we use our available resources, but also would improve or create more job opportunities, or it would ensure that we are using our machines to the greatest extent. Now, apart from this energy and transport sector services, there are also other services wherein the high temperature materials come into play. These are material processing units, the ones that we are largely acquainted with. Now, we know that to have a desired material, we need to extract it from its ore, and this we have seen in the previous slides as well. And when you have such an extracting plant or such plant wherein you plan to extract the material from its ore, you can't do it without in a large or in a major chunk of materials, you can't have it from its ore without involving high temperature. So we need to have sufficient setups and sufficient the right material used for the setup in order to increase the efficiency of this whole setup to derive the material from its ore. So this material processing, or the role of high temperature materials in the material processing, again they play two roles. One is wherein we attempt to extract the actual material that we have desired and from its ore. This material could be a pure element, or it could also be alloys, wherein we try to combine different pure elements or add some alloying elements and to create an alloy that has the desired properties and caters to a specific need. In order to do this as well, we need to have sufficient setup, sufficient large vessels that can withstand the temperature. In addition to the temperature, it is important to note that we need to have these vessels which are resistant to the corrosive environment to which they are exposed to during this operation. And along with the extractive aspect of it, along with creating the material aspect of it, we also have manufacturing techniques wherein we expose the material to a high temperature. If you look around us, we use a lot of components, and all these components at one point or the other would have gone through an high temperature processing techniques. And the devices that introduces this high temperature, or that imposes this high temperature and all those conditions that transform a material to a component, they are built of high temperature materials. And again, when we have right high temperature materials involved in this particular machine that turns the material into a component, it means that you are operating the machine in the full capacity. You are doing it in a way that efficiently uses its energy resource. Now, in addition to material processing, as a final aspect wherein, or in the final sector wherein the high temperature material play a significant role, is the chemical industries, the industries that serves us with chemicals that we use in our laboratories, or sometimes that we use in our day-to-day lives as well. In these chemical industries, like the energy sectors, we have reactors wherein we process the chemicals. You have also boilers and vessels that typically increases the temperature of the materials or the chemicals that you are processing. And again, often you might read some article that in the laboratory condition, we have found a way to extract this material in this efficient manner. So by doing this, by following these steps, we can extract this material X in a more efficient manner that is practiced in industry scale. Now, when you look into that, the key word here is laboratory setup. Now, there are several hindrances that prevents us from using or adapting this efficient approved approach that is confined to the laboratory to the industrial scale. There are several factors that impedes from adapting this well proven technique of extracting a material or creating a material in an efficient manner or extending this to an industrial scale, there are several factors that hinder us, and one of these factors is high temperature materials. Now if we take an area wherein we know that there is an well proven way to extract or to process this material, which is more efficient than there is the one that is being done in the industrial scale. If you are able to identify such a process, and then when you see what actually impedes us from using that on the industrial scale, it would be a high temperature material. There would be a role for the high temperature materials involved in it, and that is one of the reasons why one should also understand the behavior of high temperature materials, and one also should understand why one should focus on working on high temperature, not only studying on it but working on high temperature materials. Now if you are wondering what are the roles metallurgical engineers could play directly in serving the people, these are all the areas where high temperature materials are involved, and if you have an expertise in high temperature materials, in all these areas you can serve, and in all these areas there is a demand for you. Okay. Now, in addition to cutting across all these sectors wherein high temperature materials play a role, we can have a brief look on the critical components as we have seen in the previous slides, wherein the high temperature materials play a role. Now, the reason why I show this plot here is when you talk about the temperature of a material to which that particular material is exposed to, it is important to consider the lifespan of it, and that is the reason in this plot, along with the temperature to which the material is exposed to, we have the lifespan included. This is vitally important because high temperature material research is often coupled with understanding the lifespan of the material. The reason is because you can easily understand the reason for it by considering a lamp filament. Like I don't know if you have ever seen a bulb. It is usually referred to as like something like this. Like this is the filament that you have in the bulb, and your bulb will be something surrounding it. Please pardon my weird drawing, but I just wanted to get this across. It's not the bulb that it's not a tube light or something similar to it. I'm talking about a filament bulb. Now, when you have a filament bulb, or when you have one in your house, or when you have seen it working, the failure of the filament bulb is not like gradual. You won't see it is gradually the intensity of the light that it offers gradually decreasing and ultimately it fails. That is not how it happens in a filament bulb. What happens is that suddenly it's working and suddenly it is not. So it happens abruptly. Unfortunately, all the failures of high temperature materials also happen abruptly, and that is the reason why the failure or explosion of a boiler, failure of any high temperature component, it's rather catastrophic. And that is the reason why one would often relate the analysis of high temperature material with the life requirements or the life expectancy of it. Now, this plot gives us an idea of how what are the lifespans of a particular component in hours. Now, if you have a look at here, so we have a steam engine which is operating at fairly low temperature when you compare it with other space vehicles, and relatively its lifespan is quite high. Now, of course, you can also increase the efficiency of the steam turbines. You could also increase its operating temperature, but what ultimately would happen is that its lifespan decreases. And when its lifespan decreases, what it would mean for the industry is that you have to stop the whole plant, work on replacing it. You not only then stop providing energy to the people who are dependent on you. You not only do that, but you also have to invest a lot in finding the right labor and also finding the right equipments to replace the steam engines. And that is the reason we don't usually operate at full capacity. We operate at subpar capacity so that we increase the life of these components. And now, as a consequence of studying high temperature materials, if we are able to increase the life of these components, it would serve a huge purpose. Now, all these serving the purpose, or all these increasing the efficiency, as I have just discussed it in a quantitative or in a qualitative manner. I just mentioned that, okay, if you increase the efficiency of this materials, okay, if you increase the lifespan of, say, the steam engine, it would mean that it would be operational for quite some time, and this would mean that it would continue to serve its purpose for a larger period of time. In addition to that, in addition to this qualitative analysis, people have quantified how an enhancement in the high temperature material would quantitatively, in addition to the qualitative aspect, would quantitatively improve the efficiency of the output. Now, before going that, I just wanted to pose this question to you. Now, if you take the y-axis of this plot here, now the difference between this 10 and 10 to the power 2, that is 100, is 90, and we have a space here. And the difference between this 100 and 1000 is 990, I believe, or it's exactly 900. I'm sorry, it's 900, but here it is 90. But still, this plot shows equal amount of spacing between these values. I pose these questions to you. Can you answer why there is this equal spacing between these two values, even though the difference between them are quite large? It's just something I believe most of you would know the answer to this question. If not, you can have a search for it and find. Like I said, this whole lecture would be like a storytelling if I don't pose some questions like that, and that's the reason I posed this question. So just think about it. The difference between 10 and 100 is 90, and 100 and 1000 is 900, but the distance between them is the same, and what is the reason for it, and why would one prefer a plot something like that? Just think about it. If you know the answer, it's well and good. If not, just try to find the answer for this question. Now, coming back to quantitatively showing that by using high temperature materials, or by virtue of the high temperature materials, we can increase the efficiency of, or we can optimally improve, we can optimally use the non-renewable resources with that. We can see an example here. Like currently, the superheated tubes in steam rising boilers, these superheated tubes, they actually play a role in increasing the temperature of the steams. We have saturated steam, and these superheated tubes they play a role in increasing the temperature of the steams that ultimately will drive your turbines, that ultimately would create electricity. So these superheated tubes are the component that play or that experience the maximum amount of heat. Now, currently they operate at a temperature of 560 degrees Celsius. Now, if we increase this operational temperature by appropriate material to this, then it is projected that the efficiency then would become from 35% to 36.5%. That is, when we increase the operational temperature of the superheated tubes from 560 to 650. 560 degrees Celsius, so 650 degrees Celsius, that is a 90 degrees Celsius increase in the operational temperature of the superheated tubes would mean that the efficiency would increase by 1.5%. Now, you might say, okay, the 1.5% is not much of an increase in the efficiency, but if you translate into the amount of coal that is involved in producing the efficiency of 36.5% instead of 35%, it is, as it is shown here, 3.5 into 10 to the power 6 tons of coal. 3.5 into 10 to the power 6 tons of coal annually. So when you, as someone who is studying high temperature materials, now if you get fascinated by this research in high temperature materials and you continue to work on this field, and when you are able to contribute like a 90 degrees increase in the operational temperature of the steam superheated tubes, you would be saving approximately 3.5 into 10 to the power 6 tons of coal annually. And this would no doubt fetch you a lot of recognition, but apart from all this recognition, you would have contributed something directly from your material research to the society, particularly energy sector. So these are all the reasons why one would want to understand the behavior of high temperature materials. The bottom line here is, I just wanted to end this lecture with this. The bottom line here is that you might be learning about several you would have taken several courses all through your semesters in this departments. Some of the courses would be more theoretical oriented, but this high temperature material is not something like that. This high temperature material, or the course on the high temperature materials, or high temperature materials in general, as we have seen, it has huge practical relevance, and there are numerous teams who are exclusively working on high temperature material to cater the need of a particular application. And of course, if you are interested in working on it, you could become a go-to person for the high temperature materials for a particular application. And there is a wide scope, as I see it, there is a wide scope in the scientific community for people who are willing to work on high temperature materials. So think about it, and let's see ourselves in the next lecture. So thank you.